hackers, and thank you so much for tuning in today. Really appreciate you for dropping by. Today we're going to be talking about today we're going to be building actually natural systems simulations, something of the sort. I can see somebody in the chat recognizes me. I'm gonna go ahead and do my due diligence by first sharing the good words that is signing in. So if you are dropping by and you are looking for them participation points, make sure you get credits for dropping by hopping into the link right there. If you are here and this is your first time, I'm gonna quickly talk about what it is that we're looking at. We have this wonderful book that's called The Nature of Code. It's part of a series that the Coding Train has put out. The Coding Train is a YouTube channel that's run by a very cool professor who does a lot of things around creative coding as a whole. And so he's actually written a book. So we're going to be going through the book instead of going through the videos. And we are currently on the very first chapter, technically at index 0. It's the pre-chapter, if you will. And it's about randomness. So last time we were here, we only got about halfway through the book. We were working on doing these different exercises, and I think we had just finished exercise point 4. And I guess we could kind of work on exercise point 5, but I think in the nature of it being a new day, we're going to try something different. We're going to continue going on and see what else this chapter has to bring to us. So if you would like to follow along, we actually have access to a very wonderful online code editor. It's called p5.js. Well, technically, that's the name of the library that we're going to be using today. They also happen to have a code editor. So I'm going to go ahead, drop down here, and grab this link and post it in the chat. There we go. So the way this works is you write some code and then it spits things out on the right side. Yesterday, when we were running this, we actually had a little half and half thing going on. And in order to make sure that we can actually read things, I had to zoom in a little bit. So now we can only see either the code or the actual simulation running. Now, as a quick tour, can I write code to fix your broken window? I can. Can I guarantee it'll work? No, I'm not there, so I can't see your broken window. Okay, so as a quick tour, we're going to take a look inside the actual files that power this code editor. We have a few things going on. We got a HTML page, we got a JavaScript file, and then we got a CSS file. The JavaScript file is as follows. This is our driving code. There's only really 2 functions here to keep an eye out for. It is the setup function, which runs once at the very beginning, and then we've got the draw function, which runs continuously after the setup. And so this is really useful for writing down anything that is kind of moving around, and this one is really useful for writing down things that just need to exist once. Now, otherwise, it behaves exactly like normal JavaScript. So if you want to use other JavaScript functions, a lot of those things are already built in. However, the preferred way to do things within P5 is to use the functions that are defined by P5 itself. And there's going to be a whole bunch of random ones, as we'll see. Okay, so next then, we're going to take a look at index.html. This is pretty much as simple as we can get it in order to run with this library. All we need are a couple CDN scripts. So these are scripts that just connect the library to our HTML page, which means if you actually copy and paste this HTML doc into your own file, you could actually run this without using this web editor, which is really handy. You just need to actually run it like you would normal web development. But this also means that technically speaking, it's actually not that hard to make to integrate the P5 animation library into your own website. I have plans to do that for my personal website whenever I redo that. It's gonna be a little bit of time. Since there's just so many things happening in my life right now. Anyway, let's talk a little bit more about what's actually happening in the body. There's not too much going on here, which is nice. We've got a script down here, which is kind of like an anchor point. This is the thing that points to our driving code. And then we've got the main element right here, which is like an anchor element that this script is going to use to create a canvas, which is just the place that we're going to be drawing everything. And that is basically it as far as this tour goes. There's a CSS file, but there's basically nothing in there. We just want to make sure that like our canvas shows up is what's going on here. Okay, so if we want to add a new JavaScript file for whatever reason, we would need to pop in here and then grab the name of the JavaScript file and then pop over here and then add a new script and then source that to the new JavaScript file. We will probably have to do that soon, but before we do that, we are probably going to, as if there's any amount of randomness that's dictating what it is that I'm going to do next. There kind of is. Speaking of probability, the thing that we're doing is mostly, I guess, the thing about natural simulations is that they're not purely random, but they are kind of directed randomness. That is kind of the main thing that we learned from the last session. Okay, so let's get going on this section. Right now, we're about halfway through. I'm going to continue reading this out. If somebody finds that really annoying, do let me know, and I am happy to adjust our stream style so that I am less annoying. But for now, I'm going to assume that you all want to hear my lovely voice, so we're going to continue doing that. I'm going to read out loud and stop once we get to something that I want to talk about. Okay. There will come a time in your life when you don't want a uniform distribution of random values, or even a Gaussian one. Imagine for a moment that you're a random walker in search of food. Moving randomly around a space seems like a reasonable strategy for finding something to eat. After all, you don't know where the food is, so you might as well search randomly until you find it. However, there's a problem. As you may have noticed while watching your walker object in action, random walkers return to previously visited positions many times, a phenomenon known as oversampling. This could make your search for food fruitless, or at least inefficient. Hi, Shaima. Shaima? Thanks for sharing where you're tuning in from today. I appreciate that. And I am looking forward to having you on the stream. Thank you for joining. All right, I'm going to continue reading. One strategy to avoid such a problem is to take a very large step every so often. This allows the walker to forage randomly around a specific position while periodically jumping far away to reduce the amount of oversampling. This variation on the run and walk is known as the levy flight, which requires a custom set of probabilities. Though it's not an exact implementation of a levy flight, you could state the probability distribution as follows: the longer the step, the less likely it is to be picked. The shorter the step, the more likely. I guess to illustrate what it is that we're talking about with this oversampling, I'm going to go and pull up the random marker that we built from last stream. Okay, I believe this should be it. There we go. So basically, a random walker is literally like, it's a little dot that randomly chooses between at least more than one direction to move towards. And so in this example, we have a random walker that chooses one out of every 4 steps. So that is up, down, left, and right. And so it can choose any of those things at any given moment and just kind of walks towards that. So it's kind of just like bumbling around, kind of wandering. That is what the random walker algorithm is. And then this oversampling that it's talking about right here is it's talking about how it just kind of re-walks over a previous place that it has been. And so that's a problem if you want to be discovering new things, like new frontiers, or just like if you're looking for more specific things. In this case, the author talks about food, which can be bad. In this case, the solution was to just randomly take a really big step. So let's go ahead and continue reading, and we shall see. I think there's going to be an exercise where we actually do this. Or maybe we can actually implement this in our current random walker. Okay, so I'm going to continue reading now. Earlier I wrote that you could generate custom probability distributions by filling an array with some values. Some duplicated so as to be picked more frequently, or by testing the results of random. One way to implement a levy flight might be to specify a 1% chance of the walker taking a larger step. So in this example, r is equal to random 1. So random, which just picks a random number from 0 to whatever number it is, but exclusively. So it'd be exclusively just decimal numbers between 0 and 1. If the number is less than 0.01, then we're going to take a big step in a random direction in either way. Otherwise, we are going to continue taking a step 1 unit at a time. However, this reduces the probabilities to a fixed number of options, 99% of the time a small step, 1% of the time a big step. What if instead you wanted to pick a more general rule, such as the higher the number, the more likely it is to be picked? For example, 0.8791 would be more likely to pick than 0.8532, even if that likelihood is just a tiny bit greater. In other words, if x is a random number, the likelihood of it being picked could be mapped to the y-axis with the function y is equal to x. It's funny that he picks y and x as this, considering that we also used y and x for our coordinate system over here. Not a big deal, though. Okay. If a distribution of random numbers can be generated according to the graph, you should be able to generate a random distribution that follows any other curve you can define with a formula. One solution for a custom distribution is to pick 2 random numbers instead of 1. The first random number is just that, a random number. The second one, however, is what I will call a qualifying random value. This value is picked by the program to decide whether to use that first number or to throw it away and pick another. Numbers have an easier time qualifying, will be picked more often, while numbers that rarely qualify will be picked infrequently. Here are the steps for now. I'll only consider random values from 0 to 1. Pick a random number, r1, compute the probability. Pick another random number. If r2 is less than p, you found your number. If r2 isn't less than p, then go back to 1 and start over. Here, the likelihood that a random value will qualify is equal to the random number itself, just as you saw in figure 3. If r1 equals 0.1, for example, r1 will have a 10% chance of qualifying. If it equals 0.83, then it'll be 83% chance. The higher the number, the higher the greater the likelihood that it gets used. This process is called the accept-reject algorithm, a type of Monte Carlo method named for Monte Carlo Casino. The following example features a function that implements the accept-reject algorithm, returning a random value from 0 to 1. We kind of missed the beginning part of that function, so I'm going to reset this. Okay. So I'm going to give everybody a second to kind of digest that. Hi, Lily. Welcome back to the stream. I'm happy you can join us again. Let's see. I can feel a sneeze coming. I'm hoping it's not going to just like randomly jump scare everybody. All right. So I'm not actually sure how this is doing the auto accept distribution. I'm guessing, oh, so the further left it is in this number thing, the less likely it is to be picked, is basically what it is doing. So that means the ones that are higher on the right are going to be more likely to be picked. Let's see, and then we have our first random number, which is the one that would actually figure out where in this x-axis it would land. And then the probability is the same as the number that we picked. And then we grab a random second value, and then we're going to see if the second value is less than the value of the first one. And if it is, then we're going to return that number. All right. While the accept-reject algorithm does work for generating custom distributions of random numbers, this technique is not efficient. It can lead to a considerable amount of wasted computation when a large number of random values are rejected, especially when the qualifying probability is very low. When I get to genetic algorithms in Chapter 9, I'll take a different, more optimal approach. By the way, this is my favorite chapter in this book, Genetic Algorithms, because it literally is what it sounds like. Well, I guess it could be more literal if it was named something like evolutionary computing, because basically it takes the idea of genes from biology and says, whoever survives this round, we're going to grab your genes and mix it with another person that survived this round, and we're going to keep on going until we get all like the perfect genes, I guess, for whatever generation that we're going until. But for right now, we're going to be doing things randomly until we can get all the way to Chapter 9, which will be, I think, quite a few streams from now, considering the rate at which we're going. All right, so now we've got our first exercise of today's stream. We've got, our goal is to use a custom probability distribution to vary the size of the random walker steps. The step size can be determined by influencing the range of values picked with a qualifying random value. Can you map the probability to a quadratic function by making the likelihood that a value picked is equal to the value squared? Then proceeds to give us a uniform distribution of random step sizes, and then talks a little bit more about how to change that with vectors. Okay, cool. So it looks like we're going to be revisiting our Walker intelligence failing. I wonder if it's best to actually just fork this. I'm going to see if it's easy to fork this. Click on this thing. Maybe not. Click on my stuff. Click on this. Duplicates. There we go. Okay, so today we're going to do Walker 06. No funny names for this one. We're going completely functional today. All right, I'm going to give you a quick code tour of what it is that we have from the last stream. I'm going to start on the simpler side of things. This is our driving code. Not a terrible lot of things going on here. We're making a canvas, which is the space that we are allowed to draw on. We're making a walker using a walker class, a custom walker class that we were just looking at earlier. And we set the background to be 255. So we're only painting it once, and then we're drawing on top of the same sheet of paper. And then for the things that we are looping and constantly doing is we are asking our walker to take a step, and then we're then asking it to take off its camouflage and show where it is in the world. So most of the work that we're going to be doing is going to be hidden under the step function. So let's take a peek at that. Don't be afraid, there's kind of a lot going on here. Most of this isn't super necessary, which is why I wanted to kind of revisit this. So let's see. Up here, is there a way to easily collapse everything? I'm going to collapse and uncollapse these things one at a time. Okay, so the constructor, basically just a thing that it's a method, which is a function that's attached to a class. And this thing just gives it a few attributes, or I guess like variables that are going to live with each instance of this walker. Okay, so not too much going on here. All we're doing is we're just spawning in a new walker at the middle of the screen. For the show method, we've got a few things going on here. We're calling in a function called noStroke. This is basically saying whatever it is that I draw next is not going to have an outline. The next function is fill, which is basically saying the next thing that I draw is going to have something inside it, and it's going to set to be this color. If you only give it one number, it is basically going to be a number from 0 to 255, and wherever that number is how white or black it is. In this case, at 100, it's kind of like a light gray color. And we're drawing a circle which takes in 3 arguments. The first one is going to be its x location, then its y location, and then the radius, which is how big it is. Okay, and then we've got the step. So the step, we've actually extracted this out from a few other functions. So in this one, we were using it for exercise 5, which at the time was setting up like a random step size for how big its steps were going to be based off of the Gaussian distribution. The Gaussian distribution was basically kind of like a bell curvy kind of thing. It was very middle oriented, and so things that were in the middle were more likely to happen, and then things that deviated from the middle were less likely to happen. There were 2 arguments for that. One is where it started, and then the next one was the standard deviation of that. So because this is a copy and I already have all of this stuff, I'm going to chop, chop, chop. Let's see. I'm trying to remember which of these I am going to be borrowing from for our actual random walker. I think this one is choice and step size. We're going to copy this one. Whoop. Actually, I'm going to leave it out here in case we need to make any more adjustments to this. And then I'm going to get rid of these other 2. Okay, so let's name this random step 06. Actually, we can rename that better because this is talking about the levy jump. And I'm going to change my naming convention a little bit here. So for methods and functions, I'm going to try to use, I think this is Pascal case or it's Campbell case. I forget which one allows us to have the uppercase first letter or the first word. And then whichever one has lowercase first word and then uppercase second word, etc. So this one's going to be called levy jump. And then we've got all of our steps. Let's see. Actually, I think this one should be random step. And then we're going to have levy jump. And then so the levy jump is basically going to be in control of how big of a step that it is that we make. And then the random step is going to give us the direction that we're moving in. And so this is the thing that is going to require some information from levy jump. So we need to make sure we return some sort of a number. So let's go ahead and make a number here. Let's step size be equal to 0. We'll make it that for now, just as a placeholder. That way we know generally what it is that we're going to be doing. So we're going to have const step size is equal to levy jump. And then I don't think we're going to need any parameters for levy jump, since this thing is just going to be, it's just going to return the size of whatever the step is. So we're going to handle all of our random number generation inside of the levy jump. Okay, the next thing is we're going to take this step size and then we're going to toss it into random step. Now this choice thing is another thing that's defined by randomness, so we don't actually need that here. We're going to define it in here. Const choice is equal to, I'm going to set this to 0 for now. I'm going to set this to replace me. I'm going to do the same thing here so that I don't forget. Okay, so then for random step, we're going to pass in a step size. And I think that's going to be all we need there. Okay. So let's just make sure that we can at least have a random walker working. So let's actually go in here first and replace this thing first. And then for step size, it's going to be set to 0 by default. Well, I guess maybe we should set this to 1 for now. All right, chat, you're gonna need to remind me if I don't remember where this number one is. That actually, wait, you know what? Even easier, I'm just gonna put in a comment. Update or to do. Okay. So now what we're going to do is we're going to use this pair of functions that we learned from last time, which is basically we're going to take a random number from 0 to 4. So all we need to do is, or 0, 1, 2, and 3 are our options. If we do this, but the thing is that random picks floating point numbers, which means it has a lot of decimals. So we're actually going to take this, wrap this in another function that's called floor, and now we're just going to take whole numbers from 0 to 4 exclusive of 4. So that means 0, 1, 2, and 3 are the only options. And so if it's 0, it's going to move this way in the size of whatever this is. Otherwise, yeah, that's basically what's going on here. Okay, so if we run this, theoretically, it's going to break. It's probably breaking. This is a mistake I made a lot last time because if you jump is not defined. The reason why it's not defined, even though it's right here, is because it's a method and methods need to belong to classes. And so we're going to say this dot levy jump, and now it knows it's going to be referring to this. And this dot random step, and now it knows it's going to be referring to this. So if we run this, there we go. Now we've got something that's kind of running along. Little wormy thing. Okay, now let's see if the step size is actually changing. I'm going to change this from 1 to like 10. Okay, there we go. That is really oddly satisfying how perfectly it just kind of lines up on that grid. Okay, but perfect alignment isn't what we're looking for. We're looking for random jumps that increase the probability of being picked based off of things, based off of how big of a jump it is. Whew. Okay, so let's recall again. Vary the size of the random walker steps. Step size can be determined by influencing the range of values picked with a qualifying random value. Can you map the probability to a quadratic function by making the likelihood that a value is picked is equal to the value squared? Okay, so we're actually going to need to have another random number in here before we can even get to the step size. So I'm going to leave the step size at the top. I'm going to set this to 1. Just as a starting point, and then we're going to make sure that we actually update the step size before we get to the very bottom. Before we can do that, we need to have 2 random numbers. That a value is picked equal to the value squared. Wait, the step size can be determined by influencing the range of values picked with the random qualifying. Okay, so yeah, we still do have the 2 random numbers, like what is being suggested. So we're going to have const r1 is equal to random what's a good size? Our canvas size is 400 by 400 pixels. So something that is desperately smaller than 400 pixels. I think we're going to just go from 0 to 10. We'll do that. 10's a nice even number. Okay, so next thing is, can you map the probability to a quadratic function by making the likelihood that a value is picked is equal to the value squared? Oh, okay, if that's the case, actually, we need to make this a much smaller number. So we're going to make these both 1s, because we're going to be looking exclusively for numbers that are less than 1, because at 1, that would be 100%, right? And so basically what it's saying is probability. I'm just going to do P. Let the probability be equal to R1 squared. I don't remember how exponents work in JavaScript. JavaScript exponent. Okay, so it's just like Python then. Because otherwise, I think the up caret is actually a bitwise like operation. So it would like change a number in the binary thing and just like shift it to the left or to the right. I don't remember which one it shifts towards. That's super important because we found out what our exponential thing is. Okay, so now we've got the probability. Actually, I don't think we even need an R2. I think we just need an R. And then now we just need to have the probability. Oh no, it does want another qualifying number. Okay. So then we just need to make sure that the probability is greater than R2. Da, 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 da. Okay, so that means step size. If R1, no, if probability, the thing that we were comparing it to should be on the left side, I think. Wait, clean code, where should variable being compared to be? I want to make sure I set a good example for you all. Okay, and I remember there was a recommendation. Okay, there we go. So the variable should be on the left side. If we want to follow the clean code convention. So the variable that we're comparing is p, and we want this to be greater than r2, which is our qualifying variable. And so if p is greater than r2, then we're going to take this as our step size. Step size is equal to r1. And actually, we can just return this immediately. I know this is kind of inefficient, but I think it's a little more readable if we do this. Or maybe it is better for us to do this instead. Step size, qualifying random value. I'm going to set this to be a constant as well. Random value. And then we don't need anything to describe what its step size is. And then this is the probability. Or maybe it's even better to just be like actually verbose, I think, as far as clean code goes. Or verbose should be good there. And then we only need one comment for that. Okay, I'm seeing a question in the chat. Since I'm new to this incredible matter, if only I had some basic background in JavaScript, what should be my next step before diving into the nature of code? Honestly, this book does a really good job at kind of onboarding you, even if you don't have much experience with JavaScript. I don't remember seeing you in our last stream, but let's see. The book goes through what object-oriented programming is, which is wonderful. That is, I guess, like the thing that describes what this class is and why there are methods in here and what the word this means. So honestly, I think the nature of code is honestly, I've said that a lot now, is a pretty good place. Sorry, I just want to tighten up my microphone. It looks like it's trying to wiggle a little bit. I don't know if you can see that. The nature of code is a good place to start, even if you don't have any background in JavaScript. It goes through and explains everything, basically. And it does it in a very meaningful way. Thank you, Lily, for sharing. Okay. Keep the questions coming if you have them. Keep on helping each other out in the chat. You all are awesome. Okay. So I'm going to go back in here and... Okay. So we've now renamed R1 into step size. So we can just return step size. Otherwise, we're going to have to actually regenerate our thing. So I think what we're going to do is actually we're going to put this step size out. We're going to keep on regenerating levy jump until we get a good step size. Or maybe what we'll do is we will return 0, return step size. And then instead of putting a loop in here, we could put the loop out here instead. Step size is equal to this dot levy jump. I don't know what the best way to do that is for actually making this super clean. I think for now, since I actually do really like having a very readable step function, I'm going to actually put the loop in here. So we're going to make a loop for, actually, no, we're not going to make a for loop because we don't know when we're going to get a number that is good enough. So what we're going to do is we're going to make a while loop. And so now we'll need some sort of thing to fit in here. What we need to know is whether or not that step size is going to be greater than 0. And so I've chosen that because, well, I don't know what happened to the indentation here. Got so weird. We're going to set step size. We're going to actually move this up here. Change this to a let, so that means it's just a variable. We're going to grab a random number from 0 to 1. And then as long as it's not 0, then we're going to continue. If it's less than 0. Oh, yeah. So the reason why we chose less than 0 is because that means for this, if we don't have a valid number, we could just put in -1, and that will mean that we are guaranteed to keep on, I guess, like running around in this loop. So now I just need to add in these two over here. Oh, I should actually move this in here as well. Whoops. Let step size be equal to -1. And so since we can control like the initial starting state of this, we can set it to be an impossible number that will never be generated within the random function. And that guarantees that -1, for the very first iteration of this loop, -1 is always going to be less than 0. So that means we know this loop will run at least once. Okay, and then, so the very next thing we're going to do is we're going to generate a random step size. And then we're going to create a random qualifying random value, which is the thing we're going to compare our probability to. And then our probability is going to be calculated by not multiplying R1, but actually step size. It's not multiplying, we're actually taking the square of it so that it's a quadratic value. And then we're going to change this to probability. So as long as probability is greater than the QRV, we're going to return the step size. Otherwise, we're going to keep on looping and looping and looping. I don't think we're ever going to get out here. But if we do for some reason, we're going to get -1. I'm realizing now that this isn't even best practice as far as clean coding goes. But at the moment, I'm not going to get too hung up on this because I just want to see what the rest of the exercises are. Let's see if this actually works. So this thing works. It should mostly just be having very small steps and then it'll randomly jump pretty far. What I'm realizing forgot to do is we forgot to actually make the step size a little bit bigger. So, it's going to be really hard to tell if the step size is increasing from like 0.5 to like 0.7 or whatnot. So to make things really dramatic for the step size, we're going to, well, let's take the exponent of it. We're going to make it a relatively big number. No. If you take the square of a number that's less than 1, so like you're going to end up with a smaller number. So what we're going to do is we're just going to multiply this by 10 then. So then that should make it a much more dramatic change. Okay, there we go. It's kind of moving really fast. We can see that there's some numbers that are kind of close to like evenly spaced, but they're kind of off a little bit. So I hope you're into like mildly irritating art. Maybe let's just scale this by like 5. Maybe it'll look less jarring. Yeah, there you go. Very smudgy kind of blob right there. But I think we got the spirit of the thing. Even if this code is not my proudest moment. Okay, so let's move on. That is incredibly smooth. I'm hoping we get to do that. Smoother approach with Perlin noise. A good random number generator produces numbers that have no relationship to one another and show no discernible pattern. As I've hinted, however, while a bit of randomness can be a good thing when programming organic, lifelike behaviors, uniform randomness is, as the single guiding principle, isn't necessarily natural. An algorithm known as Perlin noise, named for its inventor Ken Perlin, takes this concept into account by producing a naturally ordered sequence of pseudo-random numbers where each number in the sequence is quite close in value to the one before it. This creates a smooth transition between the random numbers and a more organic appearance than pure noise, making Perlin noise well suited for generating various effects with natural qualities such as clouds, landscapes, and patterned textures like marble. To illustrate the difference between Perlin noise and uniform randomness, consider figure 0.4. The graph on the left shows Perlin noise over time, with the x-axis representing time. Notice the smoothness of the curve. The graph on the right shows noise in the form of purely random numbers over time. The result is much more jagged. So it's not left and right because I have the screen a little bit smaller, so it's top and bottom. But we can see here that this one is like a very chaotic like seismograph, whereas this one is a much more natural looking thing. Like you could kind of imagine this being like a mountain, but like if you imagine this as a mountain, like that would be like stepping on needles as opposed to mountains. Yes. Yes. Perlin noise is a very cool randomness thing. A while back, I used to work for an organization that was working on lanterns, and so we did some workshops on that. And so lanterns, like naturally, you want to start making something with like fire patterns, right? And so I remember writing a lesson on using Perlin noise to make realistic fire effects for those lanterns. It was a lot of fun, and I got to learn a little bit about the math behind Perlin noise. It's a little more complicated than I was expecting, because it uses like the mathematical like series kind of like calculations, like the kind of things that like calculators do for approximating irrational numbers like pi. They do that kind of stuff, but for Perlin noise, which is pretty interesting. There's also some really cool, a lot of game dev tutorials talk about using Perlin noise, which is, I mean, it makes sense for like terrain generation and just like randomness things. It's also a very, it's one of the options for if you're into like modeling on like Blender or like texturing things. Perlin noise is going to be something that you'll see there. But that is neither here nor now, I guess. Maybe in a future stream we'll talk about we'll actually explore that a little bit more. For now, let's keep on reading. Ah, so Ken Perlin, absolute legend, actually came up with this thing while working on the movie Tron, which is a movie that was ahead of its time as far as visual effects history goes. Um, but yeah, developed in the 1980s, develops wow, sorry, was working on the movie Tron in the early 1980s, developed his original noise algorithm in 1983. He later received an Academy Award in Technical Achievement for this work. The algorithm was designed to create procedural textures with computer-generated effects. Procedural refers to generating the visual elements algorithmically rather than an artist manually designing them. Over the years, a variety of other flavors of noise have been developed by different authors. Some notable ones are value noise, Worley noise, and simplex noise, developed by Perlin himself in 2001. You can learn more about the history of Perlin noise at Ken Perlin's website and some of its variations. What is simplex noise video on the Coding Train website. I actually want to see what this website looks like. I don't know, chat. How brave are we feeling today? Expired certificate. Okay, so yeah, it's a really old looking website, and it just straight up does an implementation of this. Is this by any chance? Ah, so it's written in C. Not a big surprise for a very classic computer graphics thing. I'm assuming that's C. Or C family language. That is pretty cool. I think it's really funny when like you ran into like a legendary programmer who like implemented some awesome things and they have like a website that's very simple like this. It goes to show like where they put their focus. It's definitely not on recognizability. Or maybe it is on recognizability. Ah, either way. Okay, let's keep on going. The P5JS library includes a function called noise, which generates smooth random values. While the noise function is inspired by Perlin noise, it's not an exact implementation. Instead, it belongs to the value noise category and was originally adapted for processing due to its optimized performance for real-time creative coding sketches. This function produces an output similar to Perlin noise, but differs in its technical details. So for all intents and purposes, we could use it as the same thing. It just isn't done the same way. The noise function can take 1, 2, or 3 arguments as noise is computed in 1, 2, or 3 dimensions. I'll start by showing you one-dimensional noise. Say you want to draw a circle on a canvas at a random x position. Out of habit, you might use the random function. Now, instead of a random x position, you want a smoother Perlin noise x position. You might think all you need to do is replace random with an identical call to noise like so. Conceptually, this is what you want to do. Calculate an x value that ranges from 0 to the width according to Perlin noise, but this isn't the correct implementation. While the arguments to random function specify values from minimum to maximum, noise doesn't work that way. Instead, its output range is fixed. It always returns a value from 0 to 1. You'll see in a moment why you can get around this easily using the map function, but first let's examine exactly what noise expects you to pass in as an argument. One-dimensional noise can be thought of as a linear sequence of values over time. For example, very small changes from 5 to 3 to 4 to 6. To access a particular noise value, you need to choose a moment in time and pass it to the noise function. So for example, at slice 3, we would be getting 0.364. There we go. The next step is to use a variable for time and ask for a noise value continuously in draw. So we set time to be 3, and then we set n to be equal to noise, and then we just print it. It's not quite there. It just prints the same value over and over because it keeps asking for the result of noise at the same points in time 3. If the time variable t increments, however, you'll get a different noise value each time you call the function. It is conventional to start with an offset of 0, but this is arbitrary. Function draw, and then we increment it 0.01. So if you use a bigger t value, then it skips further in time. So a t value of 0.1 is a bigger jump, whereas a smaller jump is that. So if you want a smoother thing, you can generally just like change time by just a little bit as opposed to changing time by a lot. Okay, so let's see. I wonder where the next exercise is. Ah, here we go. I was just going to work on doing this if we didn't do that. I think we can re-engineer this based off of what it is that he's been describing. But let's actually get there properly first without skipping. I've made problems by skipping textbooks before. Or not textbooks, but just like skipping ahead and reading. Anyway, noise ranges. Once you have noise values that range from 0 to 1, it's up to you to map that range to whatever size suits your purpose. The easiest way to do this is with the map function, which takes 5 arguments. It's going to be a lot, but I'm sure there is meaning in that randomness. Not randomness, in that number. First is the value you want to map. In this case, it is n. This is followed by the value's current range, minimum, and maximum, followed by the desired range. So if we have a range, the current range followed by the desired range. Okay, so I'm going to go ahead and make a new file. Let's make a new file. Okay, let's save whatever it is that we had here. We're going to make a new file. It's going to be called Island Floor. It's a funny name once again. All right. So we're going to be actually taking a look at the console. Actually, you know what? Before we do that, I'm actually just going to just write down how map works. So we have got map. The first value is the variable that we're changing. And so it changes it in place. And then the current min, which I'm going to abbreviate to cmin, cmax, and to desired min, desired max. Okay, just in case we forget it later down the line, just writing that down there. In this case, while the noise has a range from 0 to 1, I'd like to draw a circle with an x position ranging from 0 to the canvas's width. So we take our value n, which is the noise that we want to scale it with, and then we take it, we know that n, because it's attached to noise, is always going to be between 0 and 1. We actually want to scale it between 0 and the width of the screen. And then we're going to pop in our ellipse, which is defined by all of this stuff. So the only thing we're doing is changing it so that the x value is the only thing that's changing, and then it's just going to sit at about y of 180. And then 16 by 16, this is basically just like the x and y, like the height and width dimensions of the ellipse. I'm not sure why you decided to do an ellipse instead of a circle, because you basically just define this as the radius. And then we increment by 0.01. And so he did this, attaching it to Perlin noise. And so instead of taking like the jagged steps that ours was with like the discrete things, we've got like a very smooth thing going on over here. It's really funny. If you leave the stroke on, it kind of looks like it's 3-dimensional and kind of just like wiggling to get closer to you. I imagine if we did this Perlin noise walker and then made it so that the radius slowly got bigger, it would be interesting. I want to see when the next exercise is because I'm kind of looking forward to coding again. Okay, so we're pretty close, but before we do that, we're going to do a little side quest. We're going to do the thing that I was describing earlier, where it'd be funny if we made this thing get bigger. So it dumped us on index.html. Let's just see if this thing runs properly first. Okay, so it is running. So what we're going to do is we're going to look for where the ellipse is. It looks like he decided to re-engineer it to be circle indeed. So instead of having it start at 48, what we're going to do is we're going to have this be set to a variable. So let's set this to, I'm going to put this at the top until I can figure out what scope it is that we need it at. Let this be radius is equal to 0. So we're going to make it kind of fade in from nothingness. And then now we need to add in some logic to make it so that as we move forward in space, so we can actually probably just use piggyback off of this. This dot, well, I guess it's not attached to the radius. We should probably actually attach this to the constructor right here. Okay, so earlier, I'm just going to call this out. I'm not sure if you noticed it, but basically this number, t, like the timing thing, is supposed to be like the starting seed. And so the reason why the tx is starting at 0 and ty is starting at 10,000 is so that because if they both start at the same time, then instead of moving around randomly kind of like in the x and the y direction kind of like smoothly, what it would be doing is it would be moving in the x and y direction at the same kind of like point. And so it'd be like very diagonally, just like kind of zigging up and down diagonally, which is not what you would want to do. And let me demonstrate that after I adapt this properly. This dot radius plus equals 0.01. So we're not actually going to be using the radius. This isn't being called anywhere yet. So none of the changes that we've made do anything yet. Yeah. So if we actually set this instead of 10,000 to be 0, it should just zigzag diagonally, which seems to be pretty much the case. And so that's why we have that step. And by the time that this thing hits 10,000, it's basically on a completely different curve altogether. So we're not going to have to worry about that at all. All right, now let's see if we can update the radius a little bit. I think the last thing for us to do is to just pop in this dot radius. So this is pretty similar to the walker that we had earlier, except instead of having it in a different file, it's just the same thing, just a little lower. It starts off so itty bitty, but now it's kind of getting bigger and bigger. Oh, it kind of like drew like a hare or like a four-legged animal there. Looked pretty cool. Okay. I can see him getting closer. Me and my impatient butt is like, maybe I should have gone back and like increased the step size. That is really satisfying to kind of watch. I can't wait to just like have like a portfolio site where I just like have one of these like random animations just like playing in like the hero page of my website, or just like not even like my specific website, but just like in general. I feel like, well, I mean, the only thing with like having this on a portfolio site is this like there's only so many. Well, it's not so much that there's only so many that already exist. You just need to find a way to make it more interesting than taking one of the very common patterns that already exists. I don't know. This doesn't really give me the indication that I was like kind of hoping for, where it seems like it was getting closer to you. I think it's probably because the radius isn't increasing fast enough. So I'm gonna just run this one more time. Now it's gonna be moving 10 times faster towards us. Okay, yeah, that kind of feels like it's getting a little faster at me. I don't know if it's just me though. I'm getting a little uncomfortable now. But yeah, okay, cool. We did it. All right, let's keep on moving. let's see. This is the map. So it took the noise variable that was scaled from 0 to 1, and then to the 0 in the height. We've already kind of explored that. Okay. Requires 2 new variables. We need to keep track of 2 different time variables, one for the x and one for the y. That makes sense. Something else odd about these variables. Actually, I think we already discussed that. Yeah, because the noise function is deterministic, that means, like, as opposed to like the random function, if you run the random function twice, it automatically picks a new seed. And so for Perlin noise, we have to, I guess, like more manually change the seed for that so that it isn't so obvious that it's already all been like predetermined. Meaning it would only move diagonally. Yes, we've already checked that one out. Yes, and I think this is a pretty good graph for that. Well, of course it is. This book was written by somebody that was much cooler than me. All right, in truth, no actual concept of time is at play here. It's just a useful metaphor to describe how the noise function works. What we have is space rather than time. The graph in figure 0.7 depicts a linear sequence of noise values in 1D space. In a line, values are retrieved at the specific x position, which is why you'll often see a variable named Xoff, Xoff, in examples to indicate the x offset along the noise graph rather than t for time. Okay, so if you want to be technically more correct, you would do Xoff instead of t. In the Perlin noise random walker, the result of the noise function is mapped directly to the walker's position. Create a random walker, but map the results of the noise function to the walker's step size instead. Okay. So I think I'm going to bring this back up. This is the one that we had just borrowed earlier and modified very slightly. I want to move this over to the right. Okay, I'm not going to move it to the right. Since I'm logged in over there, I'm going to open it up over here. More stuff. Here's the copy. So this is the same thing. Yep. All right. So what we're going to do is we're going to add in, instead of t.radius, we're going to call this ts for size. Let's give it a random seed of negative 10,000. Yes. And then so instead of radius, we're just going to change everything that... well, I guess we could have just kept it as radius and then just changed this thing to be... Oh, I'm so silly. Almost super silly. Okay. This dot radius. So we actually do need... this dots... Oh, yeah, I guess we don't actually need to initialize it with a this dots x down here, or up here. So we're just going to do... I'm just going to set it to R so it looks like it's actually matching the rest of this stuff. Just for the sake of conformity, you know. And instead of mapping it to heights, let's map it to... like 50 or something. That way the max size of this is only going to be like 50 pixels big. And then so instead of this.ts, this is going to be this.r. So if we run this, oh my god. Look at how much it's changing. That's kind of looks like it's kind of like they got a heartbeat that's like beating really fast. Kind of like one of those like sci-fi horror things. Oh, the reason why I was doing that so fast is because our stepper was just really big. So this will be less jarring. That's still kind of uncomfortable, honestly. I'm not a big fan of that. But, I mean, we finished the exercise, I think. Okay. So let's take a look at two-dimensional noise. Having explored the concept of noise in one dimension, let's consider how they can also exist in a two-dimensional space. With 1D noise, there's a sequence of values in which any given value is similar to its neighbor. Imagine a piece of graph paper or a spreadsheet with the value for 1D noise written across one row, one value per row, per cell. Because these values live in one dimension, each has only two neighbors, a value that comes before it to the left, and one that comes after it to the right, as shown on the left in figure 0.8. Neighboring values similar along one dimension, neighboring values similar along two dimensions. Two-dimensional noise works exactly the same way conceptually. The difference, of course, is that the values aren't written in a linear path along just one row of graph paper, but rather fill the entire grid. A given value will be similar to all of its neighbors above, below, and to the right, to the left, and along any diagonal, as in the half of figure 8. If we were to visualize this on graph paper with each value mapped to the brightness of a color, you would get something that looks like clouds. White sits next to light gray, which sits next to gray, which sits next to dark gray, next to black, blah, 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 blah. And so this is Perlin noise, where each pixel is its own thing, is its own cell, and that's how we get this wonderful randomness that's not purely static. This effect is why noise was originally invented. If you tweak the parameters and play with the color, it may look more like marble, wood, or any organic structure. Actually, I think we use a different kind of noise for wood. I think we use the Voronoi noise or whirly noise. There we go. So whirly noise looks more like that, which is pretty freaking sick if you ask me. You can imagine this is really good at making like kind of like slime and very like other organic looking things. But it looks like it can also be used for like rocks and such. Cellular noise. Yeah, I think that's a pretty appropriate thing. I have no idea what the folks who came up and like invented this kind of noise were on, or not necessarily on. Sorry, that's really inappropriate. But more like the amount of thinking that you would need in order to be able to come up with these kind of noise algorithms. Absolutely insane. Okay, so noise detail. Noise reference explains that noise is calculated over several octaves. Calling the noise detail function changes both the number of octaves and their importance relative to each other. This in turn changes the quality of the noise values produced. So by octaves, I'm not entirely sure what it's talking about. Let's take a peek-sees. Gotta look for noise. I think it was noise detail? Yeah. Adjust the character of the noise. Perlin noise is created by adding layers of noise together. Yep. Okay. So remember earlier how I talked about like how Perlin noise's implementation is actually based off of like math series and stuff? This is where that kind of comes in. And so I guess like the more octaves, the more layers, blah, 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 blah. And that allows us to get finer grained details. By default, it only uses 4 octaves. And so I guess you can treat it as kind of like a blurriness scale. And so the left one is more blurry than the one on the right. And so the one on the right has a higher amount of octaves, or I guess like detail there. The pattern on the right is cloudier than the pattern on the left. I guess it depends on what your definition of cloudier is. Let's see. Where is the one? Here we go. The right side. So that one is stroke C, which is determined. Where's the one on the left side? There we go. Noise detail of 0.25. Actually, wait, what's the first argument supposed to be? Ba-ba-ba. Of course, the noise will use 6 octaves, and each octave contributes 25% as much. So basically, each octave is this is how much influence it has on the next one. So this one, it has a whole bunch of octaves, but they aren't that influential. And this one has fewer octaves, but they are more influential. And so that's the thing that allows us to get more details. Okay, that's really cool. I guess if you're curious as to what the Berlin noise, I want to see what the math function for this looks like again. I remember it doing something with calculus. Oh my gosh. A pre-calculated permutation table. Dang. That's not what it is I was looking for. Ah, here we go. Implementation takes gradient vectors, computing the dot products between gradient vectors and their offsets. Oh, here's the actual function. Smooth step. You know, I don't really have the brain cells to interpret this right now. I'm going to revisit this another time. All right. Love how organic and chaotic Voronoi noise is. I'll have to drop slate. Oh, thank you so much for dropping by. I'm hoping to be able to stream some more. We'll see how that goes along with the other things that I had to do. But yes, please take care. Sleep tight. Thank you so much for dropping by the stream. It's been a pleasure. For everybody else, you're stuck with me for the next hour. Okay, let's keep on going. If you wanted to color every pixel of a canvas randomly using the random function, you would need a nested loop to cycle through rows and columns of pixels and pick a random brightness for each. Note that in p5.js, the pixels are arranged in an array with 4 spots on each: red, green, blue, and alpha. For details, see the pixel array video on the pixels track on the Coding Train website. Okay. I imagine if you're using the random value, it's gonna be freaking awful to look at. Like usually there's a lot of very high contrast things, which kind of like hurts the eyes a lot. Let's see if it actually runs this. Okay. To color each pixel more smoothly using the noise function, we can do the same thing, except instead of doing random, we'd call noise, and then we would have to map it so that the noise, which is from 0 to 1, is now from 0 to 255. It's a nice start conceptually. Calculates the noise value. Problem is that it won't have a smooth, cloudy quality because incrementing by 1 through the noise space from 1 pixel to the next is too large of a jump. Remember, with 1D noise, we jumped only by 0.01 per frame, not by 1. I'm assuming it's talking about... Ah, yes, it's talking about the step, because the step between each pixel would be 1, right? And so actually what you would need is to be moving by 0.01 instead. And so, yeah, what he's going to end up doing is he's going to end up setting a separate X offsets, separate FY offsets, instead of using the iteration variable right here. Okay. I have to confess I've done something rather confusing. I used 1D noise to set 2 variables, controlling the 2D motion of a variable. Then I promptly moved on to using 2D noise to set 1 variable, bright, for controlling the brightness of each pixel on the canvas. I didn't even notice. Where's the noise? Oh, right. Okay. So yeah, you could actually add in more arguments to noise, which is good to know. That is a really funny thing. I actually didn't even pay attention to that. That's probably because I'm skimming over his code. The way to accomplish this is to use 2 offsets to pull values from different parts of the same 1D noise. While in the 2D noise example, both of these start at 0 because we're looking for a single value for a given point in a 2D noise space. It's actually navigating two separate noise paths, whereas the pixels are single values in a 2D space. So functionally, they are kind of similar, I guess. Except if we use two-dimensional Perlin noise, it creates two separate tracks where they each have their own kind of seed. That's why he's able to start at 0. But if you would just call the noise function twice, it would be on the same kind of track. I think that's what it is that he's trying to describing. Okay, so. Oh, that looks cool. I'm looking forward to getting there. But first, we've got to do this. It sounds like, yeah, we're going to be implementing the color of everything on a page. Play with color, noise detail, and the rate at which they are incremented to achieve different visual effects. How are we doing on time? We've got another 35 minutes. I think that's going to be enough to check out these 3 exercises. Let's just quickly see if there's anything else. Okay, so I think we can safely spend most of the next 35 minutes kind of doing this. And let's see how far we can get. So first thing we're going to do is we're going to go to new, make a new thing. I like to run this just for the sake of resetting my mind so that I remember what it is that we're actually going to be making. So we're going to set the background color to be 255. I don't remember which way is dark or bright. Okay, so now we've got something that's basically super bright. All right, so the next thing we want to do is we want to draw on the X and the Y, and we also know we're going to need 2 offsets. So we're going to let X off is equal to 0, let Y off is equal to 0 as well. We know in the loop, excuse me, that was a sneeze that was like an hour in the making. We know we will eventually need to do X plus equals some sort of step size. So I'm going to go ahead and put step size is equal to 0.01. Don't mind me actually using the proper constants notation of doing like a screaming snake's case. If you don't know what screaming snake case is, it's basically snake case, which is where you use underscores between each word for variables or functions, and then the screaming version just means that it's like fully caps. All right, now we've got Y off, step size. There we go. Okay. And now I know for a fact we're going to need to have 2 forms of loops. So I'm going to have this first one be a for loop. Let X is equal to 0, X is less than. I'm going to actually take a reference to what it is that he was doing up here. Ah, yes, the width, of course. X plus plus. And then inside here, we know we're going to have a Y is equal to 0. Y is less than width. And then, no, not width, because the Y is up and down. Okay, there we go. And then I'm pretty sure we're going to have to actually put in our noise here. Yes. So I'm going to take some inspiration here. Let bright is equal to map noise. X off, Y off, 0 to 1, 0 to 255, because that's the max brightness. And then we're going to do this. X plus Y times width times width times 4. Times 4. Okay. The X and Y for each pixel position. Why isn't it just X and Y? Why is it X and Y times width? Where does the width come from? Hang on. Oh, width is how wide the thing is. So why are we multiplying y times the width? Now why are we multiplying it by 4? um, I'm gonna sit and think on that while I continue copying everything else down. Pixels index equals bright. Oh, I think I forgot to define pixels. Load pixels. I bet you he actually explains how pixels work on this video right here. I don't think we're going to watch that today. We're going to try to infer what we can because we are absolute G's. I'm seeing that pixels is pink, which usually means that it's like a reserved kind of like variable name, like width and height are variable names or attribute names. So I'm assuming pixels seems like a pretty reasonable thing to be kind of special like that. It's great. Oh, right. Okay, so pixels are an array that looks something like this, where the first thing is the brightness, or sorry, is red, green, blue, and then opacity. I think actually that was mentioned earlier, and I just kind of forgot about it until just now. So the very first index is red. So then, just to make things consistent, I'm going to do this. Woo! 2 and 3. Oh, right. The last thing is the alpha value, which we want this to be maxed out so that it is not at all opaque. Otherwise, like whenever you have like a... Wait. If all of the RGB values are the same, that means we're going to be getting basically like grayscale colors, I think. All right, let's see what that looks like. Okay, I'm pretty sure that's just about what it is that we would need. Let's run this thing and see what happens. Oof. Load pixels are not defined. Oh. I also missed a thing that says... Load pixels. Update pixels. Okay, I'm not really sure what it is that I was expecting, but that doesn't really look smooth to me. Let's take a look at what's going on here. Okay, so we know we're not doing the random function right there. We're actually replacing it with the noise that is being scaled there. And then we know that... Pretty sure this is right. I think it's the index thing that's wrong. So let index is equal to... Oh! Okay, wait. So the index is a singular value. And so that's just grabbing whatever the pixel number is for whatever location it is looking at. Could I just leave this as x plus y? Nope. Okay, so it definitely needs to be multiplied by something. I'm not even sure if that's what it's supposed to look like. Let's take a look at how this one was done. Okay. X offset there, Y offset here. We've got the double loop. We've got the brightness. We've got sets. I don't know what this is, what this function does. Oh, he also doesn't put it inside the draw function. Oh, that's because it only runs once. So maybe let's try moving this into the setup function. I don't know why I thought that would change anything. I should have had a feeling it was only going to give us one frame. Okay, let's look up what the set function does in P5. Sets the color of a pixel or draws an image to the canvas. Easy to use. It's not as fast as pixels. We use pixels to set pixel values. Okay. Update pixels must be called after using sets for changes to appear. I've got 4 very tiny black dots. I don't know if you can even see them. That's pretty cool. Hey, yo. We got a straight up picture in there. Cool. Okay, so we know that we're not actually going to worry about doing set. I'm not sure why you would use set ever then, considering pixels exists. Okay. Boop, 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 boop. You keep on getting a peek at academic paper I'm trying to read. Yeesh. All right. I should like to make it so that this thing eventually gets to see every part of the screen. What if we just did like a... Heh. Heh. I'm just kind of plugging and chucking random things now. All right. I am going to move this back into draw though, because I like the idea of having an animated literally anything. I don't like the idea of looking at things that don't move, you know. That is kind of still deeply unsettling. Why isn't it going to the full height or width? Maybe I do need to read more into how pixels work. Yo, somebody made a QR code thing? All right, let's take a look at this example. Oh, okay. Cool, I guess. That is a really funny project. Okay. So yeah, there's the tint, image height, video. This doesn't seem to have anything to do with pixels though. Oh, this is the first video of the entire track, that's why. So let's look at the pixel array. Let's look at the example here. Y is height, X is width. Pixel density. Load pixels, update pixels. Index is that magic formula again. Hmm. So if we read this, what happens? Oh my gosh, that is super staticky. But at least it fills the whole thing. So why are we not filling the whole thing? I might have to give up here and take a look at the suggested answer. Okay, that was a lot more code than I was expecting. I feel less bad about not doing this. Okay, that's pretty cool looking though. Makes like a nice like weather map kind of thing. So I would assume, yeah, these are for the controls. Randomize the button. Clicked. All right. Let's see. What is it that he did differently here? Got the X and the Y offsets. Oh. So silly. Okay. That's still not quite what it is that I was looking for. But that was definitely a step in the right direction. All right, so basically all I needed to do was actually move this in here so that it would actually get reset. So as far as the next thing goes, this is the hue, that's the color. Step size should also be in draw. Well, the thing is that we're not actually changing the step size. I mean, I could try doing that and see if that changes anything. Because the thing that I'm trying to figure out is like, why is it that we're getting 3 copies here? And why did it stop animating? I appreciate the attempt at to troubleshoot, help me troubleshoot though. Oh, he used sets once again. Okay. I think for the sake of getting some color in here, I'm just gonna multiply these by some random numbers. Hey, now we got this really green looking thing. Okay, maybe we multiply that by like a smaller number. All right, that one's not as hard in the eyes. We'll go with the nice magma looking thing. Okay, I think we've spent long enough on this. I'm going to take a pause on this project right here, and we're going to move on to the next thing. Because we have free will and we are not beholden to absolutely follow this, especially since we're not doing this for a grade. So add a third argument to the noise. Oh, we didn't even actually do this exercise properly with the noise detail bit. I wonder what he did. Did you do the noise detail bit? You totally did. Oh, and attached it to the slider. So extra. I appreciate the extra. Honestly, I'm really excited for trying this one. Use the noise values as the elevation of a landscape. Although I'm kind of worried that this one actually just straight up, it looks like it's using like an actual like WebGL kind of things. I'm going to take a poke in here. And I'm going to hope it doesn't use an actual shader. Okay, it totally doesn't. But It's doing a lot. I'm scared. Okay. I'm gonna take a peek in here. I'm cheating. I'm sorry. I am curious as to how you got the freaking 3D bits. Render the landscape as a grid of quads. Okay, so quads and vertices, these aren't things that we're expected to know yet. So why did you bring this up? I think he's just saying very generally that we could do this to check out like the elevations of a landscape. Okay. I am going to very quickly go through and finish reading the things after this exercise, and then when we come back, after we finish reading these, we're going to take a peek and see if we can do a two-dimensional version of this instead of getting this overly awesome 3D-dimensional version. All right. So I've suggested several uses of Perlin noise in this section. I assigned the smooth values of 1D noise to the position of an object to give the appearance of wandering. With 2D noise, I generated a cloudy pattern by using smooth values on a plane of pixels. It's important to remember, however, that Perlin noise is just that, values. They aren't inherently tied to positions or color. Any example in this book that has a variable could be controlled by Perlin noise. When I model a wind force, for example, its strength could be controlled by Perlin noise. The same goes for angles between the branches in a fractal tree pattern, or the speed and direction of objects moving along a grid in a flow field simulation. Flow field simulations are so freaking cool. Oh. And also this one, it's so smooth. I'm kind of curious as to how complicated this is. There's no way it's only one line of code or one page. Oh, I guess if you're actually smart about it and you did like rotations. I forget that you could do rotations. So it's a rotation based off of the lines. That is awesome. Okay. Oh, because it's recursive. There we go. Recursion. We love recursion. Except for when we have to make it. All right, I want to take a look at how complicated this is. Do you think this is going to be multiple files, or do you think it's going to be like 100 lines of code? The last one was less than 100 lines of code because it was recursive. All right, let's take a look at this one. Ooh. Yeah, no, it's got 3 different files. This one's going to be crazy. Okay, the first one's only less than 100. The next one is also less than 100. And there's no way the driving code is less than, or is more than 100. Yeah. Okay. That is fun. That is really cool. All right, I'm going to delete those things since we're not looking at that. Just as you can overuse randomness, however, it's easy to fall into a trap of overusing Perlin noise. How should an object move Perlin noise? What color should it be? Perlin noise. How fast should it be? If that becomes your answer to every question, keep reading. My goal here is to introduce you to a universe of new possibilities for defining the rules of your systems. After all, those rules are yours to define, and the more possibilities at your disposal, the more you'll be able to make thoughtful, informed decisions, choices. Randomness and Perlin noise are just the first stars in a vast creative cosmos that I'll explore in this book. As mentioned in the introduction, one way to use this book is to build a single project over the course of reading it, incorporating elements from each chapter as you go. One such possible project is a simulation of an ecosystem. Imagine a population of computational creatures living in and around a digital pond, interacting with each other according to various rules. At the end of each chapter, you will find the same prompt. My goal is to provide ideas on how to incrementally expand your own simulated ecosystem using the concepts explored in that chapter, but feel free to invent your own. The ecosystem project. For your first step, develop a set of rules for simulating the real-world behavior of a creature building on top of principles from the random walk or other noise-driven motions. Can you simulate a jittery bug that flies in unpredictable ways, or perhaps a floating leaf carried by an inconsistent breeze? Start by exploring how much you can express a creature's personality purely through its behavior. Then you can think about its visual characteristics. Here's an illustration to help you generate ideas for building an ecosystem based on topics covered in this book. Watch how the illustration evolves in each subsequent chapter as new concepts and techniques are introduced. The goal of this book is to demonstrate algorithms and behaviors, so my examples will almost always include only a single primitive shape, such as a circle. However, I fully expect that you have creative sparks within you, and I encourage you to challenge yourself with the designs of the elements you draw on the canvas. If translating designs into code is new to you, the book's illustrator, Xana Marsh, has written a helpful guide on drawing for code, which you can find in the appendix. All right, let's see. How are we doing on time? We've got currently 17 minutes left. So we have two different options. We have the option of building like a terrain generator or building some like a random walking bug. Now, let's see. I personally am kind of erring towards building a like terrain generation because last time I tried to do that, I couldn't figure out how to do it. So I'm hoping this time I will, because a while back, Coding Train had a coding challenge for making a 404 page, and I wanted to do something with that. I did not indeed end up finishing that. So let's see if we can do something. I don't know that we'll have enough time to actually do it, but let's try. Okay, so as far as creating Perlin noise goes, I want to create a line with multiple points. So let's take a look at what the P5 reference for lines looks like. I think I already have. No, I don't. P5 reference. Okay, so it draws a straight line. Oh my gosh. Oh, the three-dimensional thing just draws quads, which is this thing right here. Okay. Well, that makes me feel a little less good about not being able to do the three-dimensional terrain generation. I'm a little upset. I want to go look at this again. Oh, the thing that translated was... It was the camera. It wasn't the actual thing itself. Calculate the height values based off of a neural network. That's kind of crazy. Wait, where's the neural network pull up? I think I need to go read up on neural networks a little bit more, because I'm not sure where that's happening. Okay. Let's see. Oh no, he never got back to cleaning this part up. Let the current elevation be blah blah blah. Okay, yeah, this is definitely making my head hurt. Okay, so here's what I'm going to do. I'm going to go back over here, pop back into the notebook, and I'm going to look for where he graphed. Yes, there should be one where that was being graphed. I'm going to grab that and see if we could just play with this a little bit. Noise. So let's save a copy of this. Instead of T, we're going to call this X off. Oh, lol. He ends up just doing that right here. Okay. Well, let's just make this a nice 400 by 400. Okay, cool. Now we can make this, save this as our own copy. Okay. So what I want to do is I want to be able to grab everything. Actually, let's try to understand this first. This thing says it's no fill. Then it sets a stroke of 0, but the stroke weight of 2. I don't remember what the difference is between those. All right. What happens if I hide this one? Okay, so it ends up being very swollen. What happens if I try to give this a fill? Fill. Let's give this a 150 maybe. So this should be a nice... On one hand, that is incredibly smooth. I like how many frames per second that is. On the other hand, that's not at all what it is that I was hoping to do. So I think what we're going to need to do is we're going to need to make sure that there is a vertex point that's always being drawn over here, and a vertex point that's always being drawn over here. So let's take a look at how this shape thing works. So we add a vertex. Off of the noise. So there's the offsets, and then we're just graphing the Y. And we're adding it offsets here. And then we're adding, I'm not really sure how it's like adding, I guess like how it's moving. So we know that this thing is iterating across the width of the screen. We know that this is just going to be a noise value of 0 to 1 times the height. And so what this is doing is it is, where's the I being used? I is being used as the X value. Okay, and then the Y value is being used, is being generated from this. And so as the I iterates all the way to the right, it draws one single frame of what the previous one. It's just one frame. One frame of a full, like, ziggy-zaggy thing. Okay. And then on the next time the draw cycle starts, how does it know what the previous thing was? Because the X offset is consistent. Because if the X offset was non-deterministic and random, then we wouldn't have the illusion of it moving from right to the left. Okay. So that solves that. I think what we need to do is we need to add a vertex at O and 400. O and actually instead of height, sorry, instead of the hard number, we're going to do height. And so this is going to be the bottom left corner. And then we're going to add one at the very end. And this one's going to be width by height. And so the rationale for this are those two aligned? I don't actually know. I'm going to use my phone to check. Yeah, that's pretty much aligned. Okay. So this one will put it in the bottom left. So this one will put it on the bottom right. I can't believe I got that first try. Okay. Okay, cool. So we have got a pretty cool looking mountain range in the background. How much time do we have left? Okay, we've got another 8 minutes. All right, let's see if we can get another layer that's a bit smoother. Maybe we'll make that one green. And then we get another layer. Not necessarily another layer, but I wonder if we can make an inverse of this thing so we can color the sky a different color. Or maybe even easier is we don't even change that, like get the inverse. We just change the backgrounds to be a rotating thing from 0 to 255 that cycles back once it hits 255. And so what we can do is we can set let background be 0. Background R. Let's background G. That background. Actually, no. If we want it to be kind of like an orangey hue, the only thing we actually need to set is, or as a variable, is the red color. And so everything else can be constants. So then the green could just be, G could be like 50, the const red. Sorry, B could be like 50. And then we should get like a reasonably like colored thing. So right now what we're doing is I'm just trying to make the color for this thing a little more interesting. So fill, instead of giving it one value, we're going to give it 3 values. I'm going to just make this R. Okay, so now we've got R, G, and B, and then we're going to set this to 255. Well, I think it defaults to being full opacity anyway. And so what we want is this thing should be, yeah. Oh, I didn't actually want to change that. I wanted this to be, we'll leave this at 150 for now. I wanted to change this to be R, G, and B. Well, now we know it's kind of like a really dark greenish color, actually. So I'm going to lay off the green a little bit. Let's see what color that comes up with. It's a very dark blue, which I think is appropriate for night. So now what we want to do is we want to make it so that this I was gonna say it's just like plus R, but let's actually make this like a full rotating thing. So if we want to, it's probably easier. Hang on, I'm thinking. Okay, no, we will need another function for this. Well, we don't need another function, but I think it's tidier to have another function. We're gonna have this thing be like a looping kind of color. We're gonna call this the sun background sun. Background sun. We'll call this the sky color. Okay, and so the sky color is going to be determined. We're going to set up the RGB in here, and then before we set the R, we actually want to make sure if R plus T is times 10, so that it actually moves a little faster, is greater than. Actually, let's just set this to be the new. Let's just call this red. No, that's a reserved word. R, new R. We're gonna call it new R, NR. Okay, so we're gonna make sure we set this thing to NR, and we're basically just gonna do a bounds check on this thing. So if new r is greater than 255, then what we're going to do is we're going to reset r is equal to 0. And then we're going to let nr, and then we're going to set nr is equal to r plus t times 10. Okay, cool. So now if the combined value ever ends up over 255, then we'll just reset then we will subtract 255 from this. Let's just do nr minus equals 255. So if it's ever over 255, we'll just subtract 10 from it. And then let's see, is r being updated anywhere? No, it's not. It's just being used for this just once. So then is there even any points to having r in here? I don't know why I'm over-engineering this so much. Oh. Oh. Oh, yeah. Sorry, I just saw your comments. Yes, this is procedural content generation, or simulating natural systems, is a little bit more accurately. So right now I'm just trying to make this look a little more like a landscape, and so I wanted to make the sky color kind of fade from dark blue to more of like a warmish red, and I'm foolishly kind of over-engineering this thing. I think let's just put the background back over here. Why was it doing that earlier, actually? R plus T. We'll just do this for now. I think I'm going to be running out of time anyway. And we'll make it by 10 so that we can see it change a lot faster. So it's changing by 1 pixel color at a time. So we should be getting pretty close to, yeah, something a little warmer now. I don't remember what happens if it scales all the way up to the top. I'm going to scale it by 100. That way it's just like super fast changing, just so that we can go through some iteration. Okay, that was kind of sad. We didn't actually really get much of a blue in there. So I'm going to change this down. So that's really red. How do we make yellow? I forgot how to make yellow. RGB for yellow. 255, 255. Oh, so we need to bump up the green, actually. 150. I think that's a little too much green. Okay, so if we wanted to actually get like the proper colors for this, I would need to change all of the R, G's, and B's a lot more. But I am out of time for the stream. I'm actually a little over time. I need to give a shout out to whoever's going to be running the next stream. And I forgot who's going to be doing that. So let's take a peek in here. Next person is going to be running Intro to SQL. And it's going to be run by... I don't know who's going to be run by, actually. But this is a good opportunity for you to go and hang out with somebody different. Thank you so much for hanging out with me today. I will be posting the things that we made on stream today in the Discord, just like under the old announcements. Thank you for tuning in, and I hope to see you all very, very soon. Have a fantastic GHW. All right. Cheers, everybody.